Good morning, everyone. Today we're going to do some exercises on velocity and acceleration based on what we said on the video on velocity and acceleration, which is already uploaded. So following up on that video, we can read the first example of exercise. We suppose we have a spherical ball sitting on a table. So we have a table. We put a spherical ball in the middle of the table, so point P. The table is 6 meters long, so we know the length of the table L is 6 meters. And for some reason, the ball starts moving, suppose to the right, at velocity v0, which is 35 centimeters every 3 seconds. And then we need to find the time at which the ball reaches the edge of the table here and then fall off the ground. Basically, we don't worry about what happens next when it's falling, but we want to know the time that it takes to travel that distance. So let's see the solution basically. So we know that the ball has to move half of the way because it was just half of the table. It was in the middle of the table, so it needs to move half of the table, and this is 3 meters. So we need to, if you want delta x is 3 meters, we need to find the time. So time is delta x over delta v, or v if you want, x over v, space over time, space over velocity, because we remember that velocity is delta x divided delta t, at least the instantaneous, well, the instantaneous velocity in a interval of time, if you want. So we need to use this formula here, and we know that we have x is 3 meters, but the velocity is 35 centimeters every 3 seconds, which means it's 35 centimeters over 3 per second, which means is 0.35 over 3 meter per second. We want to use the natural unit, meter per second. So we know that time will be equal to length x divided by v, which is 0.35 times 3 meter per second. And this is easy to see that the meter cancel out as it should, and then the time we can calculate it is 9 divided 0.35 seconds. And then you plug in this number in the calculator and you see whatever number it is. It will be a bit larger than 27 seconds. Okay. Okay, so this is first exercise. Second exercise. So we have a car. Let's read it through and let's sketch a graph. So we have a car traveling between 2 points, A and B, and it's we have the time 0, which is 6 a.m., and then we have the time 1, the time of arrival, which is 9.35 a.m. Okay, so we know the time, the total time, and then we have this. We know that the speed at which it travels in each section. V1 is 90 miles per hour. V2 is 30 miles per hour, so it'll be slower, and then V3 is 100, quite quick, miles per hour. Suppose we travel in each section with the same speed, so we abruptly change the velocity at the end of each section if you want. To complete, we want to know the length of each section. Supposing that x1 is equal to twice x2 and x2 is equal to twice x3. So this is x1, which is twice x2, which is twice x3. Okay, so, well, this is A and this is B. And this is B. x1, x2, x3. And we want to find x1, x2, and x3 from this setting. Let's see how we can do it. So first of all, we know that the total time t1 plus t2 plus t3 is equal to 3 hours point 35. This is hours. This is ours. Because it's 9.33 a.m. minus 6.33 a.m. This is the same, so this is just 3 hour. Sorry. This is, yes, 6 a.m. So it was 6 a.m. So we know that it's 3.35 hours, which we convert in seconds. So an hour is 60 seconds times 60 minutes times 60. So it's 360 seconds. 1 hour. 1 hour is 360 seconds. So we convert this in seconds times 360 seconds. But then we know again that t is equal x divided by v. And then we have therefore that t1 is x1 divided v1 plus x2 divided v2 plus x3 divided v3. And this is equal to 3.35 times 360 seconds. Of course, x1, x2, and x3 are 3 variables. We have a relation for that. Otherwise, we wouldn't be able to solve this equation. So we change everything in x1, and we know that x2 is half of x1. So x1 divided 2, v2, and x3 is 1/4 of x1 because it's half of x2. And this is 3.35 times 360 seconds. Now we need to collect x1 because it's a variable, and we need to replace v1 in, if you want, miles per hours. But actually I want to do an extra step. So okay, we can solve it in miles per hour. Yes, 2 times 30 plus 1 times 4 times 120. This is x1. These are the velocity in miles per hour. Miles per hour. But this is meter. We know that this is in meter. So we need to do a conversion. 3.35 times 360 seconds. So to solve this problem, we need to calculate what is a mile per hour in meter per second. So we can do here with the green. 1 mile per hour is 1.6 kilometer every 360 seconds, which basically is 1.6 divided 3.6 meter per second. So we need to remember this conversion factor, mile per hour in meter per second. Okay, so we can therefore this is cancelled out with the meter per second. We have seconds and seconds, but we need just to stick in the conversion factor, which is 3.6 divided 1.6 because it was divided by. So again, we do a little arithmetic here. So we need to find the common factor of these numbers, which is can do it here. So we know this. So x1 is equal to 1 over 90 times 480. And then this is 480 plus 8 plus 90. And this is a number that we need to multiply for 3.6 divided 1.6. And then from this equation here, we can find out what x is, and we have the solution of the problem. Again, we can write it up here if you want with a big set of number, which I'm not going to do the calculation for. You can do it the way you prefer, but basically this is the time 3.60, and then we multiply by 1.6, we divide by 3.6, and then we divide it by 578, which is the sum of the denominator, and we multiply by 90 times 48, and this is in seconds. So this is in in seconds, in meter, sorry. We find seconds goes away, so we find the meter of this, the length of this section x1, and then we do x2 is equal x1 divided by 2, and x3 is equal x2 divided by 2, and therefore we find the solution of this example. So again, we were neglecting the numbers that we can plug in a calculator if you want, or if you like to do math in your head, you can find a quicker way to do it, or the exact way to do it if you're quick and good on math, arithmetics. So, but it doesn't matter at the moment. We are doing just physics. So let's concentrate on how do we solve it. So we have an equation for time. We use the known relation with time and space and velocity. We plug in, we substitute this equation in time. We have an equation that can be solved if we remember that x1 is equal to x2 divided by 2. Sorry, x2 is x1 divided by 2, and x3 is equal to x2 divided by 2 again. Because then it's an equation with only x1, which we find here, up here, and this is the solution of the exercise. Okay, so enough for this exercise number 2. Let's go to exercise number 3. Let's read it. So we have an object moving at each clock, and we register its position at each clock beat, which happens every 10 milliseconds. So the clock updates every 10 milliseconds. We register the position in 11 position, or some position in A and B configuration in 2 different settings. And with this position, we want to find the average velocity and graph the velocity over time, and then find who has the largest acceleration, if any. So first of all, we want to list the delta x's, or which we have, which are delta xi, which are 10 centimeter, 12, 11, 13, then there is a 19. These are all in centimeter. Centimeter, 10 centimeter, again 12 centimeter, and 15 centimeter. This is for the case A, and then we will do the same for case B. So we know that we want to find basically the velocity, the average velocity in each the average velocity. So we need to find the velocity at each step, which is again velocity is equal delta x divided by delta t, and therefore we have in the first one 10 divided by 10, but this is centimeter over milliseconds. Okay, centimeter millisecond. So 10 over 10 is 1. 10 minus 2 is centimeter divided 10 minus 3, which is millisecond, and this is meter per second. And therefore we have this is 10 meter per second. So we can find the velocity number 2. So v1 is 10 meter per second. Velocity 2 is will be 12. 1.1 velocity 2 will be 12 meter per second. Velocity 3, because basically it's 12 divided by 10 times 10. So as I said, this is turns out to be an easy calculation to do at each step. So we need V3 will be 11 meter per second, V4 will be 13 meter per second, V5 will be 19 meter per second, and then we have V6 will be 10 meter per second, and then 12, and then 15 meter per second. Okay, now the average velocity will be the sum of 12, 10 plus 12 plus 11 plus 13 plus 19 plus 10 plus 12 plus 15 divided, this is meter per second, divided the velocity, divided the number of time, 1, 2, 3, 4, 5, 6, 7, 8, divided by 8. And this is the average velocity. Okay, whatever this number is, we can calculate it, and then we will find the average velocity of our particle. Let's do the graph of this velocity. So we know that the average is this big number here, but we know how to find it, so it's not a difficult task to do. The only tricky bit here was the conversion between centimeter and millisecond if you want. Now, the graph of the velocity can be done quite easily. So we know that we are in the range of, suppose this is 5, this is 10, this is 15, and this is 20 meter per second. And this is second, and this is meter per second. So this is the graph of the velocity. So the first section is 10 meter per second for, and this is of course 10 millisecond. This is the clock that we have, 10 millisecond. So the first is 10, the first, and then we jump to 12. We abruptly jump to 12, and then we go to 11 for another bit, and then we go 13, which is a little bit more, and then we go 15. Actually, it's 19. This is a big jump, which is here, 19, and then we go back to 10, and then we have this jump in the velocity, and we go 12, and then we go 15. Okay, so every 10 millisecond we have a jump, and the difference, we know that the biggest jump is between, we can see that, right? Between 19 is this jump here. So what happens here is the biggest acceleration, because we go from 19 meter per second to 10 meter per second. It's the deceleration, which happens in basically in an instant acceleration. Okay, so this is the first exercise. The second exercise is quite similar, just we have different values for the velocity, and the spread of the velocity is different. We keep the graph there. We might need it. So the same exercise, different numbers. So the number for this exercise are 19.1. Then we have 10 9.2, and then we have 10.1, then we have 9.9, and then we have again 9.9, and then we have 10.3 and 9.7, 10.3 and 9.7. As we can see, these are all centimeter. As we can see, the velocity is still delta x over delta t. So if we convert centimeter in centimeter over milliseconds, which we know that is delta x times delta t times 10 meter per second. So in meter per second, we need just to multiply by 10, but we know that delta t is 10 again, so these two simplifies luckily, and we can use this formula to have our velocity. So the average velocity is 19.1 plus 10.2 plus 10.1 plus 9.9 plus 9.9. As we can see, with respect to before, plus 10.3 plus 9.7. This is the velocity, average velocity, 1, 2, 3, 4, 5, 6, 7. This time we have only 7 numbers, so we divide it by 7. You will find a different graph. In this case, we can see that it is 9.7, the first 10 millisecond, which is here, and then 19.1 jumps there again, but then it stays around 10.2 here, and then 10.1, and then 9.9, and then again 9.9, and then 10.3, and then we don't have another number. And as we can see that the velocity, the velocity is different, the spread is different, but the biggest jump is here again between 19 and 7, and between 19 and 10, again 10.1. But we have, sorry, between 19.1 meter per second and 10.2 meter per second, which is, if you like, is a bit less than 9. So the biggest jump is the first one, which is the biggest acceleration, instant acceleration. So as I said, the average velocity can be calculated quite quickly. Here, down here, the precise number, it doesn't matter at the moment. The reasoning that we need to follow is what matters. And this was for the second exercise, the second part of the exercise. So now we go with the last exercise. So we have a man that is running at these speeds, 10 kilometers every 25 minutes, 2 kilometers for 2 kilometers, and then so we have 2 kilometers at certain speed v1, and then we have 500 meter at v2, and then we have 10 kilometer at v3, and then we need to draw the graph. This is draw the graph of the speed and determine the instantaneous acceleration, supposing that at each change in velocity happens at the same in an instance of time. Okay, so we have solution. We have a graph, so we know that the graph is it will be a weird graph because it's in kilometer. So suppose here we've got 10 kilometer. We know that this is 5 kilometer, and then we have we need to scale it down 2.5 kilometer, 2.5 kilometer, and then if we divide it by by 2 again, 1.25 kilometer, and then we divide it roughly by 2. We have got our 500 meter if we want, which is the smallest section. And then the first time is 25 minutes. So this is minutes or seconds if you want. We know that minutes and seconds, so 25 times 60 is in seconds, is the first interval of time. And then we have 22 and 23. 22 times 60 and 23 times 60. These are the three different times, T1, T2, T3. Therefore, so T1, the first one will run 10 kilometer. So we need to do, sorry, this is the, so we need to find, yes, the velocity. So the velocity, this is the space and this is the time. So the velocity, yes, the graph of velocity is in the first 25 per 60 second. And therefore we go at the speed which is 10 divided, the speed is, sorry, yeah, 10 divided by, sorry, this is wrong. So the first 25 is 10 divided by 10 divided by 25, which is here, suppose it's here, 10 divided by 25 times 60, this is V1 in meter per second, and it stays here. And then it goes and then it goes 10 divided by 22, which is slightly larger for 500 meter. Yeah, so very short period of time. 10 divided by 22. This is the speed for another short period of time because it was 500 meter only. And then for the longest part, no, other 2 kilometers, it goes 20 divided by 33, which is here. So 10 divided by 23 for another 2 kilometers, something like this. So we have the biggest jump, as we can see, is here, which is an acceleration that goes from 10 divided by 25 to 10 divided by 22 meter per second. And the difference is the acceleration. Okay, so the acceleration will be instantaneous, so we go the difference delta v divided by delta t, which is 1025 minus 1022 meter per second square, and this is the acceleration, the biggest acceleration that we find. Okay, so the graph is simple. There are three straight sections. One, the proportion is 2 kilometer, 500 meter, and 2 kilometer. So these two segments are the same in length, but not in time. And this is the shorter. Okay, I hope you follow the exercise, and next time we will do other examples regarding the lesson that we see. Okay, see you next time. Bye.